Hello, 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 and welcome to this video on gas laws. In this video, we are going to be discussing the combined gas law. So the combined gas law states the relationship amongst pressure, volume, temperature, and number of moles of a gas under two sets of conditions. So if you look at the equation for the combined gas law, you'll notice it probably looks fairly familiar. All the different independent individual gas laws that we have learned about thus far are more or less included in this. You've got Boyle's law here, P1V1 equals P2V2. You've got Avogadro's law here. You've got volume temperature, Charles's law, and you've also got Gay-Lussac's law, pressure and temperature right here. And so what the combined gas law is doing is you're saying you have a starting pressure, volume, number of moles, and temperature, and you change them. So your pressure, volume, temperature, what is the new number of moles? What is the new volume? What is the new pressure? What is the new temperature? Keep in mind, when we're using the combined gas law, you must use Kelvin for temperature. So if you're given your temperature in Celsius, you're going to need to convert it to Kelvin using significant digits before you continue with your calculations. So where did we get the combined gas law? It's actually derived from PV equals nRT, which this is called the ideal gas law. We're going to use learn about this law in a later video. But what the ideal gas law does is it relates pressure, volume, number of moles, and temperature to a value called R, which is a constant. And R will always equal PV over NT if you rearrange that equation. So if we have, remember, a change, we change something, and we have two sets of conditions here, then R is going to be equal to the PV over NT for the first condition, and it's also going to be equal to the PV over NT for the second condition. Therefore, these two are going to be equal to each other. It's important to note that typically when we use the combined gas law, we are not going to use N1. Normally that's going to be more or less non-existent because we're using the same amount of gas. We're simply going to be changing the pressure, the volume, and the temperature. So what do you do if a factor is not mentioned in a question? So if you read a question, you don't see pressure, and again, remember, typically you won't see number of moles. You don't see pressure, you don't see volume. If you do not see a factor mentioned in a question with the combined gas law, or if it notes that that particular variable is held constant, then you're going to assume it's held constant, and you are not going to include it in your combined gas law. You're just simply going to omit it. So for example, if it says that temperature is held constant, you'd have P1V1 over T1 equals P2V2 over T2, and then this temperature, you would simply omit it from your equation when you're working it, which, if you kind of throw back to the individual gas laws, you'll note that this is Boyle's law, once temperature is held constant. But at this point, now that you see the entire combined gas law, you can see how we can hold any one of these variables constant and get one of the individual gas laws. So let's go ahead and do an example problem. The beauty of the combined gas law is all the example problems follow a very similar pattern. The most important things here are going to be your significant digits, converting to Kelvin, and making sure that all of your units match up. I do have a little chart down here on the left where you can list your givens before you begin. This is one of those things that's completely up to you. I'm more of a plug and chug person, but it depends on what your style of algebra is, if you like to write them out or simply plug them in. All right, so it says a gas at 155 kilopascals, so that's pressure 1, and 25 degrees Celsius. I'm going to go ahead and convert that to 273 plus 25. I'm going to get 298. So that's temperature 1. Kelvin. Occupies a container with an initial volume of 1 liter. I'm going to go ahead and write all these down here for you. Changing the volume, the pressure of the gas increases to 605 kilopascals as the temperature is raised to 125 degrees Celsius. I'm going to go ahead and convert that, and I get 398. What is the new volume? So that is what I'm looking for, is my new volume. So I'm going to go ahead and plug and chug here. I've got my N1, which is held constant. It does not mention it in the problem, so I'm going to go ahead and assume that that is constant. So pressure 1 is 155 kilopascals. Volume 1 was 1 liter. Temperature 1 was 298 Kelvin. Pressure 2, 605 kilopascals. Volume 2, we do not know, so I'm going to go ahead and keep the variable in there. And then temperature 2 was 398 Kelvin. I'm going to go ahead and rearrange this equation, solving for V2 times both sides by the 398 and divide by 605 on both sides. And I got V2 as 0.342 liters. The other way you could solve this is if you rearrange the equation from the get-go. So you change it as V2 equals P2 P1 V1 over P2, T2. So you can rearrange the equation from the get-go and then plug the numbers in. It's completely up to you. And that is how you use the combined gas law. And you could use that to solve for any variable in the combined gas law. It'll all pretty much be the same mathematics. You just have to make sure you keep in mind sig figs and units. So go ahead and rewatch the video and make sure you took good notes and come in with questions if you have them. Thanks.